So let us have a quick recap of what we have done in the morning. We have talked about radiation, what is radiation, what is meant by the wavelength and the frequency and the speed of light, how it is related. We have seen how uh, ratio of electromagnetic waves, what is the speed in vacuum and speed in the material. Speed in the material divided by speed in the vacuum gives the uh, refractive index. And then we have seen each photon will have an energy of hc by lambda or hf. So also electromagnetic radiation, we have seen a lot of things, and in that, one of the main thing we saw is thermal radiation is between 10 power minus 1 uh, microns to 10 square microns. This is the range of thermal radiations, correct? And one more thing we saw was visible lights where was in the range of zero point 0.4 to zero point 0.6 micrometer alone. So if you consider the visible light which is there, it's a small portion of the total. It would be a small portion of the total electromagnetic spectrum. So you see that. So it is said that we live in a world which is in the middle. Okay, middle of the length scales, middle of the time scales, middle of everything. Okay, because if you consider length scale, it can go up till picometers, the atom, and even less if you consider the photon. How big is a photon? What is the energy? What is it? 10 power minus 34 or something like that. Very small actually. Very very small. Okay, not size of the photon. I'm not saying that. Okay, it's energy packet, right? So Planck's length. There is something called Planck length, which is the smallest length which can be there. Okay, smallest length experience. It is at 10 power minus 34 or something. That is the Planck's length. Okay, I forgot that. Okay, to maximum, how much it can be? 10 power plus something. Length of the universe, right? We are somewhere in between the length scales. Okay, similar way here, somewhere in between we are there, right? So 10 power minus 10 to 10 power plus 10. We are in between that. Is it? So this is how it is. So we talked about black body radiations, right? We said black body is a body which emits all the radiation from along all the wavelengths, and at a wavelength it emits the maximum energy at a particular temperature. Fine. And also we saw that black body, which is a full-fledged in the sense it's a perfect absorber, it's also a perfect emitter. It's both a perfect absorber as well as a perfect emitter. Okay, and also we know that any body which is which has temperature more than 0 Kelvin will always emit radiation. Why? It will have electrons moving. Okay, when it has electrons moving, it means it emits radiation. So at 0 Kelvin, we have never reached, but we know there is something called Bose-Einstein condensate, which is the fifth state of matter. Is it not fifth or yeah, fifth state of matter? Right? You have liquid, gas, liquid, gas, solid, and plasma. Okay, which is, and then we have Bose-Einstein condensate. Right? Bose-Einstein condensate is about. It was predicted by Bose and Einstein in 1918, but it was actually got in 1998, and he got a Nobel Prize. I don't remember his name. I mean, not is it not? Okay, but he is a big fellow. Okay, he has got it. Okay, so he has got a Nobel Prize in year 1998 when he was able to get that in the laboratory. Okay, so yeah, these are all the things. Okay, and black body radiation, we have seen a number of things, and then we saw that the total amount of black body the energy radiated is sigma into T power 4. Sigma is the Stephen Boltzmann constant. Correct? Done. Next. Then we have to see about spectral black body emissive power. Spectral emissive power is emissive power divided by at that frequency, that particular wavelength divided by the wavelength. spectral power, how much energy that particular light is emitting. For example, you may have this white light. Now this white light is not just white light, it has all the lights coming. You can take it to a prism and you could see all the different colors of the light which is there. So now the intensity of a particular color in that particular white light may be different. It is more bluish white, or more yellowish white, or more greenish white. Which is more in that? That gives the spectral emissive power. If more green is there, then there is more spectral emissive power for the green light wavelength corresponding to the green light wavelength. How will you see what is the energy coming in that per unit area of the green light divided by the wavelength of the green light? That gives the spectral emissive power. Make sense? Sure. Now, so spectral emissive power is given by the Planck's law, and this is what is the law. Okay, so that we have seen in the morning. Now we'll continue. Now here, one of the main things what happens is, how is spectral emissive power varying with lambda, varying along the spectra, along the lambda, let us see. So if you have, see, this I will say is the EB lambda axis. If this is the EB lambda axis, and this side is the lambda axis. This side can be lambda axis. This is EB lambda axis. Spectral emissive power. Okay. Now what happens when the temperature is less? Say the temperature is around 100 Kelvin. Then it will be something like this. This is how the emissive power is. It's more on the side. This is the spectral emissive. That means actually this is the wavelength which it transmits. It's around, say this is spectral emissive power 10 power minus 6, not a 0. Not a 0. 0 is down somewhere. Okay. So this is the, this you say uh, temperature being 100 Kelvin. Okay. And this peak is around, say, this point is around 100 is the wavelength. 100 watt micrometer wavelength in micrometer, and this is around 10 micrometer. Then if I make this as 1 micrometer, and if I say this is zero point 0.1 micrometer, okay, and this one I will say 0.01 micrometer. This is 0.01 micrometer. Do it like that. Then what happens, as you increase, say it is 300 Kelvin. 300 Kelvin starts somewhere here. 300 Kelvin is our thing. Okay, so our temperature, it goes like this. This is 300 Kelvin. If this is 100 Kelvin, this is 300 Kelvin. Maximum wavelength it is emitting when it is lower is this, corresponding to this. I'm not saying proper. It's around, say, around more than 10, but less than. I'm not, don't put a very strong thing to this, okay? Because you have to calculate, okay, which is maximum. We will see that how we will calculate the maximum. So maximum may be somewhere here, and this one maximum goes somewhere here. Okay, like this. Okay, now if you join these things, I'm sorry, I have to do it this way. Let me, okay, this is somewhere. Okay, and this one. Let it go like this. Okay, so this is the emissive power which is there. Wait a minute, students. This drawing has to be perfect. Yeah, shit. Okay, done. So now if I join this, it goes as a line. Let me draw that line. This is the line along with each other. Yeah, this is perfect. Okay, this is 300 Kelvin, and the maximum thing there would be around, not here, not 10 power 10, it is near, yeah, it is almost 10 here. Okay, so it has to go much further. Okay, so it has to start from somewhere at 1, so it is 1 here. Wait, it's 1 here, and then it goes like this, and then wait, it has to be a bit lesser here. Wait a minute, friends. Sorry, here for this particular one, let me draw it here. This will be line like this. It goes somewhere this point. Has to reach. Then it goes like this. So around highest point here, highest point, which is over here, the maximum point which is over here, this is 300 Kelvin. The maximum point comes somewhere below 10 micrometer. Means we are emitting radiations. We are emitting radiation at the range of more than or nearly 8 or 9 micrometer, which is infrared. That's why you see people with infrared goggles. You put infrared goggles, you can see people in the night, is it not? They are red in color. They are not visible. You're not having visible radiations. Okay, unless until you are some mythical yogi. Okay, then you will have it. Otherwise, you will not have it. Is it not? Okay, that means you're burning. That's what he said in yogi. Yoga, he said that you get these things. Why? Because you're burning from inside. Okay, so we are not burning. Okay, so it's okay. Yeah, we are burning in fact, but burning is a different. There is a combustion process going on inside our body. Is it not? Everyday combustion happens in our body, and there's all the things which is happening, right? It's a thermal power plant here. It's a thermal power plant. Okay, and where is the combustion happening? Where is the combustion happening in our body? There is combustion happening in our body. Where is it? No, no, it's in our lungs. Ah, because there is the what to say, carbon dioxide. No, it's all through. Okay, I'm sorry. It's only the exchange which is happening in the this one. This actual combustion all through the process, is it not? I don't know. I don't know. There is combustion happening. Okay, believe me. Okay, otherwise you'll not be hot. My idea is that. Okay, I may sound like Nityananda now, but still. Okay, so this is hot. When it is hot, it means somewhere it should burn. Right? Otherwise, how will temperature will increase? Correct. So fine. So done. Next one. Another point. So as we go further, at around say like this, when we go till here, okay, at around say uh, 5,800 degrees centigrade or 5,800 Kelvin, this will go something like this. Okay, this will go something this way. Start somewhere here, then like this. This is the max. You know what I am referring to. Then it goes this way. So difficult. Okay. This one is at 5,800 Kelvin. Okay, this is at around 5,800 Kelvin. So I should actually, to make it better, I have to change this over here. I will change this. Okay. Anyhow, I'm actually wasting time. I know that. So let this be point one somewhere here. Make it nice, students. Okay. So this is the maximum, and then it goes down. It goes down like this. This is around 5,800 Kelvin. 5,800 Kelvin. This one, the maximum comes to around the, it's not here, it's over here. Right? The maximum comes to around visible radiation at 5800. What is that? It's the sun. The surface of the sun is at 5800 Kelvin. The maximum radiation it is emitting in terms of energy per emissive spectral emissivity is maximum for visible radiation. It has others, but that's less. Maximum is visible radiation. Actually, the peak comes near violet. Okay, peaks comes near violet. Okay, that's why most of the things which is coming is ultraviolet. Maximum peak is ultraviolet, but nearby we have visible radiation. That's why we have the ozone to shield us. Correct? So that's how it is. That is 5,000, 5,800. Now, when you go further, if you consider sun is around 6,000. So more ultraviolet comes. That's very important. And this one, which is there, locus. This is the locus of maximum power. Maximum power. This is lambda into T is equal to 2897.8 micrometer Kelvin. Very 2897.8 micrometer Kelvin. Like that, you can know at what temperature what is the lambda which is having. So that is called the Wien's displacement law. Okay, so let us see the Wien's displacement. This actually is the Wien's displacement law. Wien's displacement. Wien's. W-I-W-E-I-N-S. W-I-E-N-S. I'm sorry. W-E-I-N-S. Wien's displacement. Wien is a person. It's Wien's displacement. Let us look at it. That's the thing. Okay. So if you want, I'll write Wien's displacement. Write it nicely. Wien's displacement law. Displacement law. It states that the maximum, the wavelength, the wavelength at which the peak spectral emissivity, peak spectral emissivity occurs occurs at a specified temperature. At a specified temperature is given by lambda t for maximum power. Lambda t is equal to 2898 2897.8 micrometer Kelvin. We can find it out. Let us see. Done. Done. Next. Now let us understand this. Okay. Uh, determine determine the wavelength wavelength at which maximum power is radiated by a human body at 36.8, right? 36.8, right? The human body temperature is 36.8 degrees centigrade. Correct, no? 37, 36.8 ಅಲ್ಲ ಕರೆಕ್ಟ್ ಅಲ್ಲ ಅಂತ ಮಾಡಿ ಜನರಲ್ ನಾಲೆಜ್ ನನಗಿಲ್ಲದೆ ಪರವಾಗಿಲ್ಲ ನಿಮ್ಗಾದ್ರೆ ಇರಬೇಕಲ್ಲ. ಹ್ಯೂಮನ್ ಬಾಡಿ ಟೆಂಪರೇಚರ್ 37 ಡಿಗ್ರೀಸ್ ಹತ್ತಿರ ಇದೆ ಆಯ್ತಾ. 37 ಡಿಗ್ರೀಸ್ 37 degrees. Okay. Question. How do you say that? Lambda is equal to 2897.8 divided by 37 plus 273.15. ಎಷ್ಟು ಅಂತ ಹೇಳಿ ನೋಡುವ. ಅಷ್ಟೇ ಒಂದು ಐಡಿಯಾ ಕೇಳೋದು ನನಗೆ ಅಷ್ಟೇ. .34, which falls as an infrared radiation. Correct. Now, even if you see, that's why light is not seen here. Okay. If you say 1000 degrees centigrade, something is heated up, you can see it becoming red hot. Depending on that, you can say what is the temperature of that. That's how you see. Okay, so it is not that it is totally what do you call? It is totally the only the that light is coming. It is a range of lights. If you say at this one, it is not just this light. It's the peak light, but there's a range of light it is emitting. You understand? Similar at 1000 degrees centigrade also, it may be somewhere here, which has a range of lights. Make sense? So you by seeing the light, what is that? A pyrometer detects its temperature. A pyrometer detects the temperature of that, but it's staying far. It's seeing only the light coming out of it. And similar way, a device which is far away from you detects your temperature. You are going to some mall. What does he say? He'll keep a meter here and he'll say this is your body temperature. How does he do that? Makes sense. It sees what is the emitting radiation. You're emitting some radiation. So that's why I say you should not go near bad people. You have bad radiation. This is called. This is what there's one person called Richard Dawkins who says all these things. There is one great Shiv Khera, not Shiv Khera. There's another guy. What is his name? A doctor in this one, saying quantum healing. You know that? There's one doctor, Deepak Chopra. Deepak Chopra. He started something called quantum healing. What is quantum healing? Sometimes we should not go to things which you don't understand and use those words unnecessarily. Otherwise, we lose value. Deepak Chopra is a great person. But because he used something which is unnecessary, he is losing his value. You understand? So, I hope you understand. So, 9.34 micrometer is the thing. Okay, now what is the temperature? Now tell me, determine question. Determine the wavelength at which maximum power is radiated by sun at 6000 Kelvin. Kelvin. This is just a exercise. Okay. So 2897.8 divided by 6000. What is it? It comes almost in the ultraviolet range. It's less than zero point 0.4. So, sorry, it's in the violet range. What is it? 0.4. Makes sense. So by knowing what is a spectrum of the light coming from a star, we can know what is its surface temperature. We don't have to go to star with a thermometer and measure it. We cannot, obviously. What is we see it and tell. Miracle, right? We see the star and tell what is its temperature. Not just that, we tell what is it inside it. Without going to sun, we have said it is helium there, hydrogen there. How did we say that? Because hydrogen absorbs energy of a particular wavelength. We said what is there inside Jupiter. How did we say what is there in Jupiter? Because the sun's light which is coming on that is reflected back. When it is reflected back, some wavelengths are absorbed totally. So that particular wavelength would be missing in the spectrum. So we know what is the material there. Did not know this? Without going to Jupiter, how will you say what is there in Jupiter? What is there in Pluto? What is there in a far off star? Today, that not Kepler, what is the telescope? Hubble telescope. Hubble telescope has said that there is a water world somewhere. There is or if you consider our, huh? uh, no, no, no. It is a Kepler mission, I suppose, done by Hubble telescope. That's all words which are correct. Okay, that's naming. That's a different case. Okay. So now, say for example, you have one Jupiter's moon called Io. It has totally sulfur in it. How did they know it is sulfur there? They have never landed on this one and did a chemical experiment. How do they know that? But just by seeing its spectrum. It's coming out of it. Moon, what is it made out of? We can know from here. Then we cross-checked it when we went through Apollo. We checked it. Okay, so that's how the things are. I hope you understand. Okay, very interesting. These are very interesting. Okay? And you know how do you know there is a planet? It's fantastic. It's fantastic. Why? Seeing the now, how do we do that? There's something called frequency Fourier transforms. How spectrum is known, the prism what takes the light and makes it into three things. The same thing happens with Fourier transforms. You know Fourier transforms. Somebody is doing a lot of things here. Mhm. Okay. Uh, okay, sir. Sure. Okay, I will take class. So he has some technical issues, so don't worry. Okay, I have to respond to him. Is it not? December 2nd is today, is it not? Don't worry, sir. I will take class. So we'll have radiation. Today second. Yeah, today is second. So he's not having. Okay. Is that clear? So tomorrow morning I will not have class. Okay. Then you want class tomorrow morning? Yeah, you have to go fast, is it not? At 8 o'clock you have to reach there. Okay. So then next. Now I hope you got the whole sense of how radiation works, is it not? Now generally, okay. Huh? Yeah. It's not done. Okay. So we will do tomorrow, 5 o'clock onwards, evening 5 o'clock, and then day after tomorrow also I'll take class. So by Sunday I intend to complete the syllabus, radiation. Okay. Sure. Let us see. Okay. So that December 4th it will be completed. I said 25th first. I said by 25th heat transfer will be complete. Then it may into December 30th, November 30th, which is December 4th. It's okay. I hope you understand me by now. Right? Shameless person, you know. Okay. So now, next, let us understand. Okay. So now, when you consider black body radiation, okay, so the total black body emissive power, okay, the total emissive power, EB, is the emissive powers, emissive powers, emissive powers added along all wavelengths, wavelengths that are in mathematically I will say like this: EB is actually equal to integration of 0 to infinity EB lambda, EB lambda, which is a function of lambda and t, which is given by the Planck's law. Okay, Planck's law is over here. This is the Planck's law. Whatever is given in the Planck's law, when you integrate, you actually get and d lambda, you get the total emissive power. And the total emissive power is actually equal to sigma into T power 4. Black body, for black body only. It's all black body radiation, right? So this, you say the next equation number. What is the equation we have got? 5 we have got. Get this Wien's displacement law as 6. Wien's displacement law as 6. And then we have this one as 7. Make sense? Fine. Very easy. Okay.
Sir, 60 question.
Sixth,
Equation.
this is the sixth equation.
Oh,
Lambda t.
okay.
Okay. Wayne's displacement law would be the sixth. This would be the seventh. Right? Now let us do a question which is given in this one. Okay, let us do that. Okay. Now let us do one question. Okay, the question is like this. Uh, Consider, should we do that? Okay, let us do that. Consider uh, why we have to do this is I'll tell you. Okay. 20 centimeter spherical ball at, okay, let us have, I have taken something from Senja, but let us have something very important. Okay. Spherical ball at, say, 35 degrees centigrade. Let us say 35 degrees centigrade. Okay. 35 degrees centigrade. Okay. Assuming, assuming the ball to be a black body, to be a black body. Determine, determine the total emissive power. Also, determine the emissive power at, at emissive power at a wavelength or spectral emissive power. Determine the spectral emissive emissive power, power at, at spectral emissive power at point 0.5 micrometer. If the temperature, this is to get an idea, if the temperature is increased, to 1500 degrees centigrade, what would be, what would be the emissive power and emissive power, emissive power at zero point 0.5, or spectral emissive power and spectral emissive power, spectral emissive power, spectral emissive power at zero point 0.5 micrometer wavelength. Okay, this is wavelength you have to add. It's okay. Okay, fine. Let us do that. So first of all, what is the first case? What is the emissive power EB at 35 degrees centigrade? What is that? That is given as sigma into T power 4, right? Sigma is, what is sigma? Uh, Sigma is 5.70, 5.7670 into 10 power minus 8. Remember this, students, into temperature 35 plus 273.15 raised to 4. That's the answer you get, you tell me. This is just to give you an idea. What's the answer? 1.75 into 10 raised to minus 5? No, no, no. Come on. 511 24 8 what? Unit. Watt per meter square. So your body area is more than 1 meter. 1 meter square, right? Okay. So if you consider if you were at 35 degrees centigrade, you are actually emitting, you are actually emitting, okay, you are actually emitting more than 5 light bulbs of 500-watt bulb of energy you are emitting continuously. Okay. You take zero point 0.7 as the emissivity. It is in that range only. It's not very less. If not 500, it's 400. That's it. Now, can't we utilize it to produce power? Yes or no? We can, is it not? Why are we not able to produce that much power? See, we are so powerful, but why are we not able to produce that? Tell me. You have to tell me the answer. We have that much of power, and that much of power we are living continuously. Not joking. That is the range. Your body surface area may be more than much because you have. It's not plain, you know. So all the things are there inside. Okay. So that's here also. It's all the area here, everything combined together. It's more than 1 meter. So it's like 1,000-watt bulb, 100 watt, 1,000 watt is bulb only. But then why are we not able to produce energy? Can't we use a power plant? See, 1,000 watt, 1 megawatt. 1,000 watt ಅಂತ ಹೇಳಿದ್ರೆ 1 megawatt. 1 megawatt ಅಷ್ಟು ಎನರ್ಜಿ ಉಂಟು ನಿಮ್ಮಲ್ಲಿ. ಒಂದು ಕಿಲೋವ್ಯಾಟ್. 1 kilowatt is ಎನರ್ಜಿ ಉಂಟು. ಅದನ್ನ ಯಾಕೆ ಯುಟಿಲೈಸ್ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗುತ್ತಿಲ್ಲ? ಕರೆಂಟ್ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡಿ. ಬೇಗ ಹೇಳಿ, ಬೇಗ ಹೇಳಿ. That much you're continuously radiating, man. Because it is not available. It is not available energy. Availability ನಿಮ್ಮ ಇದರಲ್ಲಿ thermodynamics ಅಲ್ಲಿ. It's not available. It has high entropy. That means if all the things has to be available, then you have to stand in 0 Kelvin. Then that much you can have a particular energy, and that to the 0 Kelvin, that radiated energy, it has to be absorbed by a heat engine. Okay, and then it has to reject heat to 0 Kelvin. Then you can convert, not all, depending on Carnot efficiency. Oh, 0 Kelvin, 0 Kelvin you can do everything. You understand? All the relations, all the joining you have to do. Okay, let us do that. Don't worry. Okay, availability attend ಮಾಡಿದ್ರಿ ನೀವು. ಸರಿ ಆಯ್ತಾ? ನೀವು ಅಟೆಂಡ್ ಮಾಡಿದ್ರಿ, ಅದು ನೋಡ್ಬೇಡಿ. Exactly. Whatever we are rejecting, that much only we are receiving. Otherwise, what will happen if you don't receive? First, you will start with shivering. Will you not shiver? Understand? That is energy being produced. It's not like that. It's not like that, but you shiver. Just joking on the others. Okay. Okay. Is that clear? Okay. Now, in spacesuit, you have insulation. You have insulation. Modifications. So now, next, what is EB at lambda? At lambda is equal to 0.3 micrometer. Tell me, what is that? How do you find that? Use Planck's law. What is the Planck's law? Substitute and get it. So you can write 3.71477 into 10 power 8, which is C1 divided by lambda zero point 0.3 to the power 5 into e power C2. C2 is 1.43878 divided by lambda, which is zero point 0.3. It is in micrometer only, so you don't have to worry. Zero point 0.3 into the temperature, which is this added together, 35 to 73 plus 35. What will come? 200, 308, is it not? 308 or 308, right? 308.15, right? Minus 1. Now you tell me what is the spectral emissivity of it. First. This is just for you to get an idea. It's not very important for gate. Okay. For gate, if you do view factor, it's more than enough. Not there are other things also, but view factor is also important. Wait, I want the answer. ಎಷ್ಟು ಬಂತು 9.74 into 10 raised to 4. I'm sorry here. This is wrong. I'm very sorry. 10 power 4. That's the reason you got wrong. But anyhow, that's okay. How much you got? Yeah, obviously it is low. It can be low, it can be high also. It can be high. Sorry, sorry. It can be high. I'll tell you what is the answer. Possible. Possible because zero point 0.3 micrometer. I am sorry, I have not used this into 10 power minus 6, right? Raised to 5. This is all what you used. You did not do. But yeah, then fine. Then fine. So zero point 0.3 fine. Okay. Then this is watt per meter square micrometer. Watt per meter square micrometer. What did you get the answer as? Watt per meter square micrometer. What is that the answer you got? Tell me. 4.17. Correct. 4.17 into 10 power minus 57. So very, very, very low. What happened? You got that answer? Which one? This you should not take point. This is micrometer here. So if I take micrometer, ನೀವಿಲ್ಲಿ ಇದು 10 into 10 power minus 6 ತಗೊಂಡ್ರಾ ತಗೋಬೇಡಿ ಹೌದು ಅಷ್ಟೇ ಅದೇ ಕಮ್ಮಿ ಅಂತ ನೆನಪಲ್ಲಿ ಬಂತು ಸೊ ಔಟ್ ಆಫ್ ದಿಸ್ 511.24 per meter cube how much energy is emitted at this particular one so the energy emitted at 0.3 micrometer okay 0.3 micrometer is 4.17 10 power minus 57 0.3 micrometer no 0.5 I'm sorry 0.5 I'm sorry it should have been taken at 0.5 not 0.3 why 0.5 then what do you get no much difference yeah 4.17 ಚೇಂಜ್ ಆಗುತ್ತೆ ಇದು 0.5 ಸಾರಿ 0.3 ಅಂತ ನಾನು ತಲೆಯಲ್ಲಿ 0.3 ಇದೆ ಇಲ್ಲಿ ಬರೆಯುವಾಗ 0.5 ತಗೊಳ್ಳಿ ಏನು ದೊಡ್ಡ ವಿಷಯ ಏನಿಲ್ಲ 2.4 3.44 into 10 raised to minus 31 ನೋಡಿ 0.5 ಇಂದ 0.3 ಮಾಡೋಕೆ ಅಷ್ಟು ಡಿಫರೆನ್ಸ್ ಬಂತು ಅಲ್ಲ ಇದು ಹಾಕಿದ್ರಲ್ಲ 0.5 ಎಷ್ಟು ಬಂತು -58 ಬರ್ತದ ಚಾನ್ಸ್ ನೋಡಿ ನಾನು ಮಾಡಬೇಕಾ 31 ಬರ್ತಾ ಉಂಟಾ ನೋಡಿ ಇನ್ನೊಮ್ಮೆ ಮಾಡಿ -31 ಸರಿ ನಂಗೆ ಕರೆಕ್ಟ್ ಆನ್ಸರ್ ಗೊತ್ತಿಲ್ಲ ಸರ್ ವಾಟ್ ಎವರ್ ಯುವರ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಇಸ್ ಡನ್ ಮಾಡಿ ಅಯ್ಯೋ ಮಾಡಿ ಜಸ್ಟ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್
Correct, sir.
yes correct ಅಲ್ಲ
Yes, sir.
yes so 0.5 micrometer ಯಾಕೆ 0.5 ಹೇಳೋದು ನಾನು this is the visible radiation observe this is the visible radiation right so it is 3.44 into 10 power minus 31 into see the energy emitted wait a minute hear me students okay this calculation is small thing the concept is important okay the energy emitted at 0.5 micrometer is 3.44 into 10 power minus 31 into 0.5 into 10 power minus 6 watt per meter square. So if I mask everything and I leave only the energy which is coming at 0.5 micrometer in that wavelength, the energy what is coming is so small, whatever we think is 1.77 into 10 power minus 37 watt per meter square. Out of this much, what is coming out? Only this much. Where is the maximum? Maximum is at 35 degrees centigrade. You have to put the Wein's displacement law and see where it is the maximum. Now if you consider this, observe at 35 degrees centigrade, lambda max is equal to 2897.8 divided by 273.15 plus 35, which comes out to, tell me fast, 9.4 into 9.4 micrometer. Now substitute and find find EBW, EB lambda at 9.4 micrometer. Can you do it? Yeah, you can go to the previous slide. Next, find energy emitted at zero point 0.5 micrometer. See, there are number of people coming out. Okay, one is zero point 0.5 micrometer, zero point 0.4 micrometer, 0.3 micrometer. Everybody is carrying energy. Who is coming out? So electromagnetic radiation is like who is coming. Who is carrying the most? And how much is he carrying? Wavelength. So much energy is going off. Only this much energy. Out of how much energy is coming? 511.248 watt per meter square. At this wavelength, only this much is coming. But let us see at the maximum wavelength how much energy is coming. Tell me what is EB lambda. See, this is how you get the feel of the subject. Right? Tell me fast. So all these wavelengths are continuous. Not discrete. Complex number is remaining, is it not? Big one. Uh, but those are small ones. Complex number 2 marks. Laplace transform is that. Industry. But the major difficult ones are over, which you can concentrate and now it is all easy ones that you have to remember. What is it? EB lambda. So we'll do it again. So EB lambda at 9.4 micrometer and 308.15 Kelvin is what? C1 is 3.74177 into 10 power 8 divided by 9.4 raised to 5 into e power 1.43878 into 10 power 4 divided by zero point 0.9 minus here, of course. No minus, no minus, no minus. E power something. Okay. No minus. Okay. E power 0.9, so 9 into 9.4 into 9.4 into 308.15 minus 1. Tell me what is the answer. What's the answer? 35.49 into. So you see it's high. So what is it? It is so many watts per meter square into micrometer. Because everything is in micrometer, meter square micrometer. Now, what is EB? That means the energy emitted, okay, at 9.4 micrometer is 35.49 into 10 power into 9.4 into 10 power minus 6 watt per meter square. Watt per meter square. What is the energy? Then it is 35.54 into 9, whatever that is. So you need the, you know, at that particular response how much energy is transmitted. How much it comes? 3.34 into 10 power minus 3, correct? Minus 4. Huh. Minus 3, no? Are you sure? Minus 4 watt per meter square. Everything together comes. That is the maximum. You have to add everything, then you get the total energy. Then you have to take 9.4, 9 limited 9.4 micrometer. Yes, all change, all you add.
The entire spectrum at that temperature.
Exactly.
Total it comes to 500.
Now, if you want to see, let us see one more thing. Okay. See here, I know it's a problem, but I am not going like that. I am going with the curiosity what you have. Okay, because through curiosity we can understand things, is it not? So let us have a curiosity stream here. Okay. So, done. Now, let us see the total energy. Now, in the above problem, in the above problem, ಬರ್ತಾ problem, determine the total energy emitted emitted between lambda is equal to 5 micrometer and lambda is equal to 15 micrometer at 35 degrees. In that range, what is the total energy? Let us see. Yes, sir, has come. No, Agastya. What is the energy emitted in that range? You're painting. So EB is equal to integration of, okay, lambda is equal to 1, sorry, lambda 1 is equal to 5 micrometer and lambda 2 is equal to 15 micrometer into EB lambda into D lambda. Now, integration is difficult there. ಇಂಟಿಗ್ರೇಷನ್ ಸುಲಭ ಇಲ್ಲ, ಮಾಡ್ಬೋದಾ? ಮಾಡ್ಬೋದು. ನಂದು ಇಂಟಿಗ್ರೇಷನ್ ವೀಕ್ ಉಂಟು, ಅದಕ್ಕೆ ನಾನು ಪ್ರಾಬ್ಲಮ್ ಮಾಡಿ micrometer. It is given as C1 divided by lambda power 5. ಎರಡು ಇದೆ ನೋಡಿ, lambda power 5 ಇದೆ, ಇನ್ನೊಂದು exponential of C2 by lambda t minus 1 ಇದೆ. ಇದನ್ನು ಹೇಗೆ ಇಂಟಿಗ್ರೇಟ್ ಮಾಡ್ತೀರಾ? ಮಾಡ್ಬೋದು, ಮಾಡ್ಲಿಕ್ಕೆ ಆಗೋದಿಲ್ಲ. It is not impossible. Okay, t lambda. ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗ್ತದಾ? ಇಲ್ಲ. ಇಂಟಿಗ್ರೇಷನ್ ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗ್ತದೆ. ಆದರೆ ಅದು ಟೈಪ್ ಮಾಡುವಾಗ ನಿಮ್ಗೆ ಅರ್ಧ ಗಂಟೆ ಹೋಗ್ತದೆ. ಅದು ಸೈಂಟಿಫಿಕ್ ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಆಗ್ತದೆ, ಇದೆಲ್ಲ ಆಗುದಿಲ್ಲ. ನೋಡುವ ನಾನು. ಲೆಟ್ ಅಸ್ ಸಿ ಹೌ ಟು ಇಂಟಿಗ್ರೇಟ್ ದಿಸ್. ಲ್ಯಾಂಬ್ಡಾ ಪವರ್ -5 ಅಂತ ತಗೊಳ್ಳಿ ಒಂದು ಫಂಕ್ಷನ್, ಇನ್ನೊಂದು ಫಂಕ್ಷನ್ ಎಪ್ಸಿಲಾನ್ ಇ ಪವರ್, ಇಲ್ಲಾಂದ್ರೆ ಇದಕ್ಕೆ ಯಾವ್ದಾದ್ರು ಇ ಪವರ್ ಅದಾಗುದಿಲ್ಲ. ನೋಡಿ ಹೇಗೆ ಮಾಡ್ಬೋದು ಅಂತ. ಇಲ್ಲಿ ನಮ್ಮ ಹಾಗೆ ಆಯ್ತು, ಇಲ್ಲ ಅಂತ ಶೋರ್ ಗೊತ್ತಿಲ್ಲ. ಈಗ ಒಂದು ವಿಷಯ ಆಗುತ್ತೆ ಇದರಲ್ಲಿ, ಎರಡು ವಿಷಯ ಇದೆ. ಯು ಕ್ಯಾನ್ ಸಿ ಅವರ್ heat transfer book by, it's very difficult. There are two cases which is there. One case is what is lambda t and what is C2. Let us see that. What is lambda t? Lambda t is 9, okay, or 5 into 3000 or 300. What is 5 into 300? 1000, how much? 1500, right? And what is C2? C2 is given as uh, C2 is 1 point, yeah, it's almost comparable, is it not? No, you cannot. Uh, yeah. Integrating is a nightmare, I suppose. Quanta? Super. So integrating, you have got 270.13 watt per meter square. Using calculator, integrated using calculator. 289.9, same calculator.
289.9.
It's
Similar values.
using calculator. When you integrate using calculator, you got this, is it not? So what does it mean? The idea is this. The idea is that, see, out of how much? 511, the maximum emissivity is coming from that, in that range. Others are there, but maximum in that is that in that range. Other is in that 511, 270. So remaining is 251. The 251 comes with other things. Makes sense? So it is a small range, 5 to 15 micrometer. Correct? So that's what is this. Okay. Now, what is the emissive power at emissive power at 1500 degrees? What is the emissive power at 1500 degrees? If you see emissive power at 1500 degrees centigrade, it is EB is equal to sigma into T power 4. 1500 degrees centigrade, we have said, no? Yeah. So now do that. You will see how much high it is. 5.7607 into 10 power minus 8 into 1500 plus 273.15, the whole power 4. It will come big number. So just to have an idea. Okay, sir, we'll start before 7:15. Okay, sir, we'll start before 7:15, so I'll stop here. Okay, so it's 7:06 now. 5 minutes break we will have because next topic to go. Now, what is the answer? 5.1.51, 10 power. How come both of them get different answers? 569. Okay, I will hear what our 569 into, correct, 10 raised to 3 watt per meter square Kelvin. Sorry, watt per meter square, right? I believe Daivik now he is getting consistently right answer. It's important to do that. Okay. Next one. Another point is, after this is done, okay. Next one. What is the maximum temperature? What is the maximum spectral emissivity? The maximum spectral emissive power. Spectral emissive power happens at lambda t is equal to lambda t is equal to 287, what is it, 2897.8. So lambda is equal to 2897.8 divided by 1500. So it is around 2 micrometer. 2 micrometer. Is it not? How much is that? Around 1.8, right? 87. Correct. 1.63. 1.63 micrometer. Correct. 2500. That's right, I missed. 1.63 micrometer. Correct. So if it is 1.63 micrometer, then what you tell, what is EB lambda? EB lambda at 1.63? You tell me. Or sorry, wow, EB lambda at EB lambda at 0.5 micrometer. So whether there will be visible radiation or not, you will understand here. We are not 1.60, we are saying at 0.5 micrometer. EB lambda. So you can see it at 1500. That's what it means. It has a visible radiation coming. Getting the point? So when that black body is heated to 1500 degrees centigrade, you will be able to see it lightly, but you can see it. First you will see it red. Then it gets other colors also. But you don't get green because red is mixed with it. You get blue at the end. If the temperature is much higher, is it not? Have you seen green color coming? Black body is not there, but if it is some special type of material which absorbs other things, then green might come. Chalo, we'll stop it here, students.